The PSoC 3 and PSoC 5 devices feature a set of 4 power modes with a goal of reducing the average power consumption of the device. They are active mode, alternative active mode, sleep mode, and hibernate mode. Active and alternative active are the main processing modes, and the list of enabled peripherals is programmable for each mode. Sleep and hibernate modes are used when processing is not necessary for an extended time. All subsystems are automatically disabled in these two modes. In this video, we would focus on the sleep mode. Sleep mode powers down the CPU and other internal circuitry to reduce power consumption. Supervisory services such as the real-time clock (RTC), the watchdog timer, the periodic low voltage detection, and the sleep timer remain available in this mode. The fixed function I2C block and the comparator block also remain available in this mode. The internal local oscillator and the external 32 kHz crystal, if connected, will be active during sleep mode. When a wake-up event occurs, the system reactivates in a single phase and returns to the active mode. Sleep mode is entered by writing the appropriate code into the PM mode CSR register. Input-output interrupts, comparator, I2C address match, other supervisory interrupts like RTC and sleep timer can wake up the system from sleep mode. Also, reset sources like watchdog reset, low voltage detect, and X reset can wake up the system. The current consumption of the PSoC 3 device during sleep mode is measured to be 1 microampere. The time required for the device to wake up from sleep is measured to be 10 microseconds. At wake up, the system activates all devices and configuration that was present during active mode and begins executing code in the active mode. The project demonstrates how to enter the sleep mode and wake up the device from sleep mode using real-time clock as the wake-up source. The schematic for the project is as shown. In the project, the device is put into the sleep mode in firmware. RTC will wake the device up every second. It also generates an interrupt which updates the RTC time. The current time is updated on the LCD and device is put back into the sleep mode. A clock of frequency 1 MHz is also brought out on a digital output pin. It can be observed that the clock signal will be output on the pin only when the device is in active mode. The real-time clock component provides accurate time and date information for the system. The time and date are updated every second based on a 1 pulse per second interrupt from an external 32 kHz crystal. This 1 pulse per second interrupt also wakes up the device from sleep mode. The important APIs of the RTC component are available in the rtc.h file. The rtcint.c file allows to write the application code to handle operations every second, every minute, every hour, every day, etc. In this example, we don't have to write any code in the int.c file. We handle all the RTC operation in the main.c file itself. For more details on RTC component, refer the component datasheet. In main.c file, we enable the global interrupts and start all the components. The time read from the RTC is displayed on the LCD as shown. The RTC read second, read minute, and read hour APIs are used to read time from the RTC. The device is put into sleep mode using the CY/PM sleep API. The CY/PM sleep API has two arguments, the wake up time and the wake up source. The different wake up source macros defined are as follows. Since we use RTC to wake up the device, we select the none macro. The different wake up time macros defined are as follows. Since The RTC uses the 1 pulse per second interrupt to wake up the device every second. We select the 1 pps macro as the wake up time. Before going to sleep, it is required to save the clock configuration used in active mode. For this, we call the CYPM Save Clocks API before calling the Sleep API. The CYPM Save Clocks API would save the clock configuration used for active mode, and then it disables the PLL, changes the IMO frequency to 3 MHz, and changes the CPU clock source to IMO. The CY Restore Clocks API is used to restore the clock configuration used in active mode. This API is called immediately after waking up from sleep mode. The CYPM Sleep, CY Save Clocks, and CY Restore Clocks APIs can be found at the cypm.h file. The code written here ensures that the device enters the sleep mode, and the next second RTC will wake the device up. Then the time read from the RTC is displayed on the LCD. The device is put to sleep mode again, and the cycle repeats. The sleep current can be reduced further by disabling the debug ports. To disable the debug ports, open the Design Wide Resources file, navigate to the Systems tab, and under the Programming or Debugging option, select Debug Ports Disabled for the Debug Port Select configuration. As it can be seen, the time from RTC is displayed on LCD continuously. When the current is measured using an ammeter, it can be seen that the measured current value is less than 1 microampere for a second when device is in sleep mode, and it goes up to 1.3 milliampere when the device is in active mode. The development kit CYHC Kit 030 should be used to obtain the best power measurements. The settings to be made on the kit to achieve low power consumption can be found in the kit user guide. For more details on this code example, refer the code example document. The example project discussed in the video can be found from this zip file. You can also refer to other code examples on low power modes available in the Cypress website.